Okay, bye.
Thank you, thank you. Right, just 1 second. Okay, actually, time is up. Okay, hi everyone. Welcome to the second session of this afternoon. I will chair this session with 4 speeches. First of all, my name is Kai Luo. I'm based in the mechanical engineering department at UCL. Actually, this morning, the department has a big news, and that is we have 2 members of staff elected to the fellows of the Royal Academy of Engineering, including myself. So at this moment, I'm actually over the moon, and we're having a meeting over the cloud. So hope we can build some models to verify all this. Okay, so the first talk will be given by Dr. Sam Hatfield from the European Center for Medium Range Weather Forecasts. He'll talk about the model constructions through automatic differentiation of neural networks. Please, Dr. Hatfield.
Okay, let me open my slides. Okay, can you see this?
I cannot yet.
Right, let me try this. Okay, how about now?
Yes, yes, you are sharing at the moment.
Thank you.
Great, I'll begin then. So I will be today continuing this theme of hybridizing machine learning and data assimilation. Specifically, I'm going to talk about how we can take advantage of the differentiability of neural networks to aid in the construction of tangent linear and adjoint models automatically. So as Kai said, I'm currently a researcher at the European Centre for Medium Range Weather Forecasts, aka ECMWF. And at ECMWF, we use a 4-dimensional variational algorithm, much like the Met Office, to construct the initial conditions for our medium range weather forecasts. Now, to give a brief overview of how 4D-VAR works, we consider a window of time, say around 12 hours, and a series of observations distributed across this window. And we begin by providing a first guess trajectory forecast of what we think the atmosphere did over these 12 hours. And then we construct a cost function, which is a function of the difference between that first guess and the observations, and also a background initial forecast at the beginning. And we, through a kind of iterative minorization process, we minimize that cost function to give the so-called analysis, which is our initial state estimate for the forecast. So this 4D-VAR algorithm relies on not just a nonlinear model operator to evolve atmospheric states forward in time over the window, but also 2 more models, which are linearizations of this model. So the first is called the tangent linear model, and this model evolves perturbations of state vectors instead of full state vectors. So it is a linearization of the nonlinear model about this trajectory. We require not just the tangent linear model, but also the adjoint model, which has a number of different interpretations, but the one that I favor is that the adjoint model propagates gradients with respect to model state vectors backwards in time. So it's essential for telling us how a change of these model state at the beginning of the window will affect a deviation from an observation later on. So these 3 models look something like this. If the nonlinear model is represented as this nonlinear operator applied to the initial state vector, then the tangent linear model is basically a Jacobian of that operator evaluated about x0, and the adjoint is the transpose of that Jacobian. So this is what it looks like mathematically, and in code, this is some pseudocode showing you what TL and AD code would look like. If you look at the TL code, you can probably convince yourself that it looks like the derivative of this expression here. And the AD code is a bit more involved. I'm not going to explain it in detail, but I hope again that you can see the link between the AD code and the TL code. It is essentially the transpose. So there are a number of relations which these 3 models have to obey in order for 4D-VAR to work correctly. And these criteria provide very strong constraints which aid in developing these models. For example, this is how the tangent linear and adjoint models must be related. This is in fact the definition of the adjoint with respect to the tangent linear. Now, as for the atmospheric model itself, what's going on inside that M, that nonlinear model operator, our atmospheric models are typically decomposed into two parts. There's the dynamics, which is the resolved large-scale flow, which can be solved using a cut-down version of the Navier-Stokes equation. But there's also what we call the physics. These are the physical parameterizations of processes that go on two smaller scales to be resolved by the model mesh. Things like, for example, convection, which can occur over scales of only 100 meters, and drag due to gravity waves. So when we want to construct tangent linear and adjoint models, we have to not only linearize, we have to linearize every single subcomponent of the model. And this is particularly difficult for physics because physics subroutines tend to be very long and esoteric, but they also involve sharp transitions, sometimes even from an if statement. So linearizing physics is particularly difficult and took ECNWF a number of years to get a mature system that can be used for operations. So what I'm going to talk about today is how we can aid in this process of constructing linearized physics using machine learning. So here is the idea in its entirety. We first train a neural network on the input and output pairs of an existing physics subroutine. This is quite a common idea now, what people call emulators. So we train an emulator of an existing physics subroutine. We then code the tangent linear and the adjoint model of this neural network. And I've done that already, actually. It's quite trivial, taking advantage of the fact that neural networks are by design supposed to be easy to differentiate so that we can do back propagation. And then part 3 is to do data assimilation with these neural network-based tangent linear and adjoint models instead of the original ones. The main motivation for doing this is because I think it's quite interesting, I think it's quite cool, but I can think of a couple of advantages if it works. The first is that the neural network code is likely to be much more compact than the original, and we only have to write it once. So we could imagine writing this neural network code and then reusing it for different physics subroutines, albeit with different hyperparameters. And secondly, the neural network evaluation basically consists of a big batch of matrix multiplications. And so that's the ideal kind of thing that can be outsourced to accelerators like GPUs, which are designed to do those calculations very quickly indeed. So today I'm going to demonstrate this idea by just concentrating on one physics subroutine, which is what we call the nonorographic gravity wave drag scheme. So this scheme is active in our operational forecasting model, which is called the IFS. And to summarize the scheme, basically it represents the effects of gravity waves, which are excited by processes in the troposphere which are too small to be represented, things like convection and fronts. Those gravity waves propagate up into the stratosphere where they break down, releasing momentum on the flow there. So they essentially act as a drag that cannot be resolved explicitly by the fluid equations. So the input to my neural network would be a column of atmospheric state vectors, prognostic variables at a particular lat-long location. And the output will be wind tendencies due to these unresolved breaking of gravity waves. The neural network architecture here will be very, very simple. I've just done a fully connected multi-layer perceptron with hyperbolic tangent activation functions. And this was provided by Matt Chantry at Oxford, who's been looking into emulation independently of me. So it's a very simple neural network with no convolution or anything like that. So as I said, tangent linear and adjoint models have to obey several relations in order to be valid. The first test here, so we consider two tests whenever we make changes to ECNWF. And the first test is to test whether the tangent linear and the adjoint are coded correctly with respect to each other. And we do this by evaluating these two expressions here on the left-hand side, the right-hand side, where delta x and delta y are just two small model state perturbations. And we check whether they conform to each other to the machine epsilon, which is 16 digits with double precision. And I haven't shown this result here, but suffice to say that the tangent linear and adjoint model of the neural network that I've coded does pass this test. The second one is a bit more involved. This is what we do is we compute this value epsilon here, which compares the evolved perturbation through the tangent linear model with the difference between two nonlinear trajectories. And this epsilon must be small. If it is small, that tells us that the tangent linear is doing the right thing. Or in this case, we at least want to match the epsilon that the existing system gives us. So these are a few epsilons here. I'm showing the change in epsilon when we go to the neural network compared with the original reference. And I've shown it for 3 variables, and these are horizontally averaged vertical profiles. So anything less than 0 means that our new scheme, our new neural network based scheme, is actually better than the original. So you can see that is the case for all of these plots, except for the very top of the mesosphere for reasons I don't understand. And so to summarize, when we use a neural network for the nonlinear and the tangent linear model, we actually get a closer correspondence between those two than if we were to use the original subroutines constructed in the traditional manner. So that's good news. And for the second test, I'm going to show you some weather forecast tests. So I've run this, this neural network-based physics scheme through a 3-month-long cycled 4D VAR data assimilation experiment, and I've run forecasts from the analysis every 12 hours. And what you're seeing here is the change in forecast error when we use neural networks compared with the original scheme. So we actually get a slight reduction in the forecast skill, around 4%, which is concentrated mostly at the start of the forecast in the stratosphere. But I would still consider that to be a success because I was not expecting this system to be stable at all in the first place. So the question is, where does this degradation come from, and can we match the skill of the existing system? Well, a couple of experiments that I'm trying now is, firstly, I didn't mention this actually, but in these experiments, I did not use the neural network in the nonlinear parts of 4D VAR. I continued to use the original scheme. And so this is not actually consistent with the test I showed you on the previous slide. So the experiment I'm running now is to use the neural network everywhere, not just for the TL and the AD, but also the nonlinear model. And secondly, the emulator that we have is not perfect. It's pretty good. But of course, it's constrained by how much training data we have. So we are continuing to iterate on the neural network architecture in order to improve the emulation. And I'm hoping that one of these avenues will give us a system that is equally as skillful as the original. So I'm going to conclude there by saying that neural networks, of course, they can be differentiated trivially. And so I think they're the ideal building blocks for tangent linear and adjoint models, which we use at ECNWF to do 4D VAR data assimilation. The system that I've built so far passes both of our TL-AD tests that we use to test these new model changes. But some further work is required in order to match the forecasting performance of the existing system. So I'm going to finish there. So thank you for listening.
Thank you very much for the interesting and concise talk, and that leaves us with some time to ask and answer some questions. Are you able to see the questions in the Q&A?
Yes, I'll stop showing my slides now. Yep, I can see those. There's just one question so far.
Yeah, that's right.
Shall I answer it in text or in speech?
Maybe you can do now because we have time, actually.
Okay, so I'll read the question out. It's from Lawrence Mitchell, and he says, it looks like they do, I think he's talking about the tangent linear adjoint tests. It looks like they do converge, but do your tangent linear models converge at the correct rate? So do you get second order convergence for Taylor tests rather than just checking that the difference is small? I don't believe we have the infrastructure for doing that specific test. I think I know the one you're talking about, which is where you run the test for gradually smaller and smaller perturbations to see if you get convergence. I don't think we actually have the infrastructure to do that. And in fact, I don't believe, I could be wrong, but I don't believe we actually test that because the perturbations we work with are relatively large. So really what we care about is how accurate the TL approximation is for those finite sized perturbations. So I don't believe we're really concerned with how the TL model behaves for very small perturbations.
Thank you. And a quick question, do you classify your simulation overall as a large eddy simulation, or you just model the small scale part?
No, you're right. I didn't mention the resolution of those tests. That was actually 40 kilometers global, which is very, very much above the, very much not eddy resolving.
Okay.
Yeah.
Okay.
Certainly not. That would be down to tens to hundreds of meters.
Okay, that's great. Thank you very much. For the sake of time, we're going to move to the next